Before diving into the learning rate, we would want to first review what the learning rate is. So during the model training, the model weights are updated by based on the gradients. So the learning rate will determine the step size of how much the gradient will be applied to the weight update. So Eden, what was the question? I couldn't hear. Um, yes, my question was whether any one of you guys have used the Blossoms AI platform. I just wanted to see if anyone's having a using it right now. Yeah. Yeah, later we could discuss that part. Okay. Yes, so the learning rate is basically a hyperparameter, which is the step size determining how much we will update the model weights. So if the learning rate is high, then that means that we are updating the model quite drastically. Whereas if the learning rate is low, we're changing it in a more controlled fashion. So, and in the previous lectures, the learning rate that you guys might have learned was a static learning rate, meaning that there's one fixed learning rate, which is applying throughout the entire course of the training. But the learning rate could also be dynamic, which then it becomes a function of the time. So the basic higher level insight for this is that when you initialize the model, then the weights did not really interact with the task. So it's usually randomly initialized, or even if we are a little clever about how about the initialization, we would want to first explore before actually converging into the minima. So in order to more explore, we would want to set the learning rate, take it high in the beginning, since we are trying to update the model. If we think about the loss landscape, we would want to explore in more directions when we throughout the loss landscape, so that our model weights now do carry some information based on the interaction with the task. And as our model learns patterns that are more useful, and we want to converge to some optimum, which is a local minimum in the loss landscape, then we would want to start decreasing the learning rate so that we actually converge to the local minimum. Because if the learning rate is even high in the end of the training, there will be risk that we overshoot the minimum and are not being able to converge. So the basic insight for having the learning rate dynamic throughout the course is because of the different characteristics that the model faces throughout the training. I think there's one more chat. Okay. Right. So that's basically the dynamic learning rate strategy, which is the concept, the idea that I talked about. And so there are different strategies, the few different strategies as in this slide. The first one is called piecewise constant, is as we can see from the maybe I could. Yeah, as we can see from its formula, the learning rate is now a function of a time. So for in between particular time steps, say from the first iteration to the 50th iteration, we set the learning rate as a to a particular number, like 0.5. And then from the next 50 steps, from iteration 50 to iteration 100, then we set it as 0.7. So basically, this piecewise constant learning rate strategy is setting a predefined learning rate for each in-time step interval. So this would be the learning rate change would be more of a stepwise pattern instead of having a smooth decrease. So it's more like a stepwise pattern, which would more look like so there is no such smooth trend in the learning rate change, whereas the exponential decay is basically using the negative exponential. So now it has a more smooth decay. Whereas, as we know, the exponential decay, the decrease is quite exponential. So the decrease is steep. So visually, which this is also in the next slide, would more look like this pattern. And for the exponential decay, basically this lambda is the hyperparameter that controls the steepness of the decay. And a polynomial decay is also the shape itself is similar to the exponential, but it's the decay steepness in decay is much more less drastic, meaning it more is a smooth decay compared to the exponential. It would look like this. And then this alpha would naturally could be thought of as a counterpart to the lambda, which controls the steepness in the decay. And the beta, this would this is a hyperparameter that corresponds to the time scaling factor. So how long into the training would we like to start decaying the learning rate, which in the exponential decay, that is just the lambda is multiplied to the time step directly, but in the polynomial decay, we're controlling it using a specific we're having another hyperparameter of beta to control that factor. So when it comes to dynamic learning rate, the scheduler is more of the how we exactly will implement these dynamic learning rate strategies. So we already know that unlike in this static learning rate, we just have one fixed value of eta. But with the dynamic learning rate, this becomes a function of the time. Now, the first question would be, how would we define this time itself? Should we update the learning rate in every iteration or each step, as this first bullet point says, or should we update it after each epoch? If so, basically, the epoch is could be it is the number of iterations when all of the training data set passes through the model, which is used for the model update. So if we're using a mini batch strategy, I mean, if we're yes, this mini batch we will cover the later of this course. So the takeaway from this is that we do have some freedom in setting up this T. And also that the more student. So also we could set this scheduling of the dynamic learning rate change, not in every fixed number of timestamps, such as epoch or iteration, but also that could be based on some criteria on the optimization of progressing. If we have some validation set, we could evaluate our current model trained up to this point against some validation set and evaluate its performance. And if that performance got better than the previous evaluation, then we could further decrease the learning rate. And so there are multiple options in determining the T when it comes to the dynamic learning rate. So this is one example of the simpler schedule. Would someone would like to give it a try on which dynamic learning rate this corresponds to from the three options that we saw before? Was the piecewise learning rate, and there was the exponential learning rate, and the polynomial. Does anybody have want to give it a shot? Which one this scheduler corresponds to? Yes, it's a polynomial decay. Yes, because there was a beta, which was a time scaling factor, is set as 1, and now the alpha is -1. So yes, that's correct. Good job. Okay. So scheduler, as you can see, those hyperparameters are substituted for some value. So it's more of the how we're going to exactly implement. So scheduler is a concept that's closer to the implementation. Okay, so another scheduler example of scheduler is a cosine scheduler, or also called cosine annealing, which, as we can see, so this plot includes some, so this plot, we can see that the step decay is basically corresponds to the piecewise decay, and polynomial decay is this sky blue one, which is less deeper compared to the exponential decay. We can just there's no green curve here, but we can just use the natural exponential decay as a proxy for it. So, and we also see the cosine annealing curve. So this cosine annealing, the curve is basically the first half of the cosine wave. So I mean, in the sine curve, cosine curve, we know that when the cosine is 0, it starts at 1, and when the cosine is pi, it becomes -1. So, and the cosine curve rotates every 360 degree, which is 2 pi. So we're just using the first half of the curve. So you can think of it as yes. So, and so why would we want such a cosine, this kind of curve, and this kind of heuristic? It's the idea is because in the beginning of the lecture, the insight for having a high learning rate in the beginning was to enable the model to explore more in the beginning. So it could be a favorable property if we could set the learning rate to not drop too abruptly in the beginning, which the exponential decay and the polynomial decay, we see the curves, the learning rate starts to drop abruptly. But whereas the cosine annealing, the learning rate is being preserved in a high range compared to the other two for quite a while, and then starts to decay. So it's a more smooth and stable decay compared to the other two. And then in the end, similar to the other two curves, it starts to decrease, which corresponds to the insight which during the end of the training we would want to converge to some local minima. About that. So that we would want to converge slower and slower. If the learning rate was too high, we would not be able to converge here, but it would overshoot. So there would be a harder time in converging. So this is the basic idea. So for this cosine annealing learning rate, we basically have the control of the time on at which time step we would want this curve to converge to this shape. So we do have control of the time, which I would first. All right. And we do also have the target learning rate, which we would want us to converge to. So I would want to first mention that when trying to interpret this formula, this plot could be a little misleading. So if we try to interpret this formula using this plot, then the t would correspond to the epoch 100, because this would be the basically the end of this first half of the cosine wave. And the target learning rate, which we want to achieve in the end, would be 0, because in the end of at time t, the big T, the learning rate is becoming 0. So, and the era of this era 0 indicates the initial learning rate where we start from, which would correspond to 1 in this case. So basically at time, when time is equal to 0, the cosine will be equal to 0, which is 1. So this term together, let me know if this is hard to interpret when I write, which this whole term will become 2, cancel out, and then eta t cancel out, which results in the learning rate at time t when equals to 0 is basically the initial learning rate. Whereas when the t is equal to the big T, then the t's will cancel out with cosine of pi. It's -1. So this term is 0. So this is a entire term will cancel out. So eta t is equal to the target learning rate. So all of the t's in between 0 and the big T will follow this trend. So this is the idea. Okay. Right. So the insight that I've mentioned in the beginning was that in the very beginning we would want the model in the loss landscape to explore, because the weights in the beginning, which was initialized, didn't really represent any learning yet. But it's also possible that in the beginning of the training, the weights could be initialized in a bad region, so which is very far from any minima and could think where things can go wrong. So in that case, we would want so such possibilities also lead to the idea that before we start active exploration, we would at least want some kind of a sensible understanding of the task before start exploring. So in short, we don't want to start exploring drastically from the very beginning based on the randomly the weight in the initialized weight, but to some exploration, be cautious in the beginning, and then as the model gets some understanding of the task, then start actively exploring. So that cautious time step where we want the model to gain some initial understanding before actively exploring here is basically the concept of the warm-up. So 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 in the beginning we would want to have a warm-up period which steadily increases to its initial maximum and then start exploring and then converge in the end. So this would be the basic takeaway from this slide. Yes, so since we went over the learning rate, now we will go over the optimizer. So the concept of optimizer itself is uh, a method, an algorithm to adjust the parameters, the weights and biases during the training to minimize the loss function. So basically, the goal of the optimizer is to converge to optimal set of parameters, which so gradient descent is the foundational optimization algorithm, which we have covered, I believe, even in the previous lectures. So in this case, so gradient descent, when we talk about the gradient descent in terms of optimizer, we're talking about it as the batch gradient descent or full gradient descent. So what does this mean? This means we're using the entire training data set to compute the gradient that will be applied to the weight update. So which means that for each individual training sample, we are going to compute the corresponding loss for each sample, which here in the formula, it corresponds to this Fix. Yes, this is actually correspond to the individual loss function of the training example I. And then we are going to average it, which we're going to average it, which gives us the objective function, which we want to optimize. So in this setting, the gradient of the objective function will also be in a similar fashion computed as first obtaining the gradient for each individual sample and then averaging averaging all the individual gradients across the training examples, which that would be the gradient vector that will be used for the model update. So the takeaway from this formula is that for the batch gradient descent in this slide, we're using the entire training examples to arrive to this the gradient. So this is naturally can be very expensive as the model becomes very large. So it's basically the O of n time complexity. And so, and especially when it comes to deep learning or like where the where where the training data set can be very large, this can be prohibitively expensive. So this motivates to an alternative to bypass this high the expensive computational cost, which and if anyone have any question, please feel free to stop me. Yes, so because of the computational cost of the batch gradient descent, an alternative would be a stochastic gradient descent, where the stochastic gradient descent here, now we see that the formula changed from the previous slide, whereas to avoid confusion, this x is basically just the weight, not input vector. Right. Yeah, actually in the previous slide, it was not there. Yeah, so the basic idea from here is that when we update the gradient of the weights, now we see that it's based on fi, right? Where f was the loss function, and so fi is the loss function for individual sample, and we're getting the gradient of it and directly applying it to the weight update instead of going through the entire process of the averaging it across a lot of training examples. So naturally, the stochastic gradient descent is randomly sampling one of the data samples from the training set, which that's why we call it stochastic, which is a random. And then we update the model weights based on that one sample. So naturally, this is much cheaper in computational cost compared to the batch gradient descent, which now it becomes the constant time complexity. But since now we are computing the gradient based on one randomly sampled training example, it's more noisy. The gradient is more noisy compared to the gradient obtained by the batch gradient descent, which is accurate. But this kind of noise could, which I will discuss in the subsequent slide, this kind of noise is not always bad. It could be beneficiary in terms of training. Right. So for the batch gradient descent, this case is using the entire training data set, and stochastic gradient descent is using one training example, which are two extreme cases. So naturally, this we would want some middle ground between the two, which is basically the mini batch stochastic gradient descent. So instead of having one or the full training data set, we're sampling a batch of training data points from the training data set, and then computing the gradient based on those subset of training examples, then applying that for the model weight update. So this is computationally more efficient compared to the batch gradient descent, but less noisy than the stochastic gradient descent. So those are the middle ground. And if we see the formula, now we're having a batch of training examples, and then we are using And this is again the loss function. And then we're using the loss over those training examples in the batch in order to compute the gradient. In case anything is unclear, please let me know. Okay. Okay, so this slide is a little convoluted, but the takeaway is that when it comes to the stochastic gradient descent, also in implementation, so in terms of the time complexity, it's very cheap. Its computational cost is very cheap because it's constant time complexity. But usually in implementation, the deep learning frameworks are set up for matrix multiplication, such as they set up for GPU and also all the libraries that are heavy just to perform a stochastic gradient descent. So in other words, why would we need such an overhead in order to just compute the gradient based on one sample? So that's also one aspect that why we usually don't go with the stochastic gradient descent of one sample. So, but if we compute the gradient based on a batch of samples that compared to the stochastic gradient setting, that will mitigate such overhead. Yes, so that's the basic takeaway from this slide. Okay. Right. Yes. So now, since we went over the stochastic gradient descent, mini batch, and gradient descent concept, so all of these basically updated the model weight based on instantaneous gradient. So in a loss landscape, if we just think of it as a loss landscape, someone asked a question. Am I muted? Am I muted? Okay. Okay, so yes, yes. So yeah, we could understand this as a lost landscape, just the drawing is not good, or maybe could do a better job. So up until now, we were updating the model weights based on instantaneous gradient. So we are basically computing the gradient at this point and just using that gradient to determine the direction and the learning rate to update it. So we're only computing the gradient at this one step. But there are the concepts that I will go over soon also include the consideration of the past because in order to arrive to this point, we could have moved to this point from the previous update, like this. So instead of relying on the instantaneous gradient, the next concept that I will go over, the momentum, will also take into account the previous gradients in determining the next direction of the progressing in the landscape. And the motivation for that is because if the instantaneous gradient is very noisy, meaning that it could be very inconsistent with the previous gradients because of the noise, which could shoot to this direction all of a sudden, then that could be not useful for actually converging. There's a possibility for that. So in order to mitigate that effect, the next concept of momentum will take into account the previous gradients as well, which aligns with the concept of momentum itself, keeping this consistent trend in some kind of progression. Okay, so basically this slide is saying what I just drew is because sometimes there are noisy gradients, we would want to be cautious in the update. So instead of just relying on the instantaneous gradient that could correspond to the noise, we would want to take into account the previous gradients as well, so that we are more consistent with the past history and could lead with the aim to lead to a more stable convergence. Okay, so in this case, in terms of the formula, now we have one hyperparameter here, right? The beta, which is the in between in the range of 0 and 1. So, and we see that this formula is recursive, right? Where bt minus 1 will be basically bt minus 2 and yes, and no need to be confused why this is t to t minus 1. You can just think of this as gt as usual, gradient at time step t. So this, since this is a recursive formula, if we plug in all the functions, you can see that there will be bt t minus 1, and after some term it will be exponential and so on. So this means that the past history is impacting the current Vt, which this Vt will be substitute for the gradient. But the influence of the, as it gets more past, the influence of the more past gradient decreases exponentially. So this is exponential decay of the past influence. So which makes sense because we want to take into account the past history in terms of the gradient, but we would want to more reflect the recent history. So this formula is basically achieving that idea. Okay. Right. So the momentum here is, now we know that we're, instead of directly updating with the instantaneous gradient, which was this, now we are first computing the momentum, and then we're using that to update the weights. So now this term includes the past history, where sorry about this confusion. whereas the previous the normal gradient the formula didn't reflect any past history. So is there any questions so far? Okay. Okay. For the progress. Right. So the now we went over the concept of momentum, and now this ADAGRAD, which is basically adaptive gradient, is so the momentum that we went over is basically averaging across the gradients. So now this ADAGRAD relates to the learning rate. So, and if we try to mentally revisit the dynamic learning rate, we did introduce some dynamic change in the learning rate during the training, but we still applied a single learning rate when updating all of the weight parameters, which in terms of the formula, we even after, in this case, for all of the weights, we're applying a single uniform value of learning rate, which varies by time, but at a particular time point, this is a fixed value. Yeah. But there could be cases where some weights are much more frequently updated compared to another set of weights. One reason, potential reason, would be, as in the first bullet point, some of the weights in the neural network could be activated or associated with more infrequent features compared to some other. So a more concrete example would be, let's say we are dealing with a natural language problem. And so in the natural language data set itself, if we think about text data, then a vocabulary such as the or is would appear much frequently compared to some other vocabulary such as the Binghamton. And during the training in the high level, some weights might be more updated when the input are these more frequent vocabularies, which translate into features. And some weights might be conceptually more associated with Binghamton. So if we have a uniform learning rate that apply to all of the weights, then the weights associated with more frequent features would be updated much more compared to the features that are associated with Binghamton. So we're not giving the model a chance to update the weights that are associated with Binghamton. And yes, I hope that's clear. So so that's the basic idea, the motivation for introducing some differentiation in the weight update, meaning when updating weight 1, weight 2, the weight vector, we're not just applying a single learning rate, but applying a learning rate for each different weight, because this weight of 1 could correspond to a more frequently updated weight, whereas weight of 2 could be about that, compared to a more infrequently updated weight. Yes, so this is a higher level idea. So then how would we determine a frequently updated weight and infrequently updated weight? So that could be accomplished by the gradient. So if a particular weight has been more updated with more gradients, meaning if there's a higher magnitude in terms of the accumulated gradient for updating a particular weight compared to another weight, that means that weight was much more frequently updated. Thus, that also means that we should take more attention when updating the less updated weight. Is this clear? Yeah, we will see that in the next slide. So yeah. Yes. So this is the formula for the ADAGRAD, which the first formula is just the gradient, the loss function between the true and our output, then getting the gradient. And then this S term is basically corresponds to the accumulated gradient. And one note is that all of these are vectorized. So what I mean is that as for the weight vector, we are holding for weight 2, weight 3. Also, these accumulated gradients are which there's a correspondence between the two. So the SW1 here is basically all the accumulated gradients that were used for updating weight 1 throughout the course of the training. And another caveat is that we are squaring the gradient. And this is because we're interested in the magnitude of the amount of gradients used for training, and we don't care about the sign because sometimes the gradient could be negative. So we don't want this to cancel out when we accumulate the magnitude of the gradient. So that's why we want to get a positive number. Maybe it's worth to go over a quick human example for this. Okay, so let's assume that our weight vector is 0.5. These are all the weights. And 1, which this corresponds to weight 1, weight 2, weight 3. And then the gradient at the current time step is 1 and 0 and minus 0.2. And the accumulated gradient at up until the previous time step as T1. Let's say it was 0.04, 0.01, and 0.1. So this tells us that up until now, weight 3 was most updated, meaning in the previous example, weight 3 is associated with more frequent vocabularies, say like the or is, whereas the second weight, this is accumulated with a less frequent vocabulary like Binghamton because it was less updated. And so in order to get the accumulation based on the current timestamp, we first want to square the current time step gradient, because we don't want this minus term to make the accumulation to something negative. Then that's by definition no longer accumulation of magnitude. So we first square it, which will give this. We could just put it this. And then now the updated gradient would be the addition of this. Now, from this information, now this accumulation will be used in determining the learning rate for each weight, W1, W2, W3, through the third formula. So from just looking at this vector, we see that the accumulated gradient up until timestamp t, the current timestamp, is still high for W3 and still lowest for the second weight, W2. So if we set the eta as the learning rate as 0.1, and this is again just for numerical stability to avoid the zero division. So this term, which is basically the adjusted weighting rate based on the accumulated gradients, naturally, this whole term will be higher for the second one, which is basically this, compared to the third weight, which has accumulated the most gradients so far, because the denominator is smaller. So we are getting varying the learning rates that's being applied based on the accumulated gradients so far, which will be updated for each of these weights differently. So this was one concrete example. Okay. So yes, so basically the per weight differentiating the update for each weight is formally called a per coordinate update, and it's basically using the magnitude of the accumulated gradient as a proxy for how frequently this weight was updated. Okay, and another caveat from here is that this can be effective for sparse features, which right. So this is basically the example of the natural language processing example of the less frequent feature associated with vocabulary Binghamton compared to the more frequently occurring items such as the or is. So we are treating them differently. Right. Okay. So this our RMS prop is the name seems very different from ADAGRAD, but the idea is it's an extension of the previous ADAGRAD, which as we can see, the weight update formula is the same, but now the accumulated gradient formula has changed, because in the ADAGRAD formula, the accumulated gradient was simply updating the most recent accumulation with this timestamp's squared gradient. Now we see that the squared gradient itself is still there, but we're having a moving average. So this is basically indicating that so we remember from the momentum from the momentum formula we saw the beta, right? Which, because the function is recursive, so this, which is the beta in this formula, this would also form some exponential decay in terms of the past gradients. So, and this has an effect of, instead of just monotonically accumulating the gradients, we're placing more emphasis on the recent gradients, which is basically represented by the st-1, compared to the past squared gradients. So the problem was grad is that since we're just monotonically accumulating without introducing this variation, the learning rate can very quickly decrease because we're just squaring and accumulating again and again. But now, since we're focusing on the more recent ones, whereas the past gradients are giving influence less, the accumulation speed gets slower, which solves which is one advantage of the RMS-Propt. But also, since we're more focusing on the recent gradients, that also has an adaptability advantage, meaning that in the deep learning, we're constantly updating the weights across all the layers. So since the weights are updating and those updated weights are interacting with the task, that means the loss landscape is the terrain. If we think the loss landscape of the terrain where we're trying to converge to optimize, that means the terrain itself is shifting and changing. And that means that the gradients computed in the older terrains are no longer as informative compared to the recent loss terrains, because the older gradients computed based on the old loss landscapes are just based on history that's no longer applicable. So that's RMS-Prop, since it focuses on the recent gradients based on the recent terrains, loss landscapes, is more adaptable to tasks, to such tasks. Any questions so far about this part? Okay. Yes. So actually, yes, we will finish this and take a break, I guess. Okay. For the Adam is first of all, this Adam optimizer, many of you might have already used it because this is one of the most widely used optimizer. And this is basically the hybrid of the concept that we've covered so far. It's a hybrid of the momentum, which the momentum was averaging across, getting the weighted average across the gradients. And also ADAM is another component of the ADAM is it uses the idea of RMS prop, where the RMS prop was like the extension of the ADAGRAD. So ADAM is the hybrid of these two concepts, where we can see from this formula as well. The first formula here is the formula that we have seen from the momentum. So just slightly different in the sense that in the momentum slide, we didn't have this term, but the idea is the same. And we're also, this second term of accumulated gradient comes from the RMS prop. Sorry about that. And there's another trick which Adam introduced, which is the bias correction. And the reason for this is because, which applies to both respectively, but in the beginning, when the V t minus beginning, the V is starts as 0. And let's say at gt minus 1, the gradient was 0.1, and the beta was, which this determines the influence of the history, was 0.9. Then when we try to, and this VT is going to be used to update by plugged in this should be, yeah, that could confuse. Okay, so at time point t equals 1, the true gradient is 0.1. So if we were using the normal stochastic gradient descent approach, then this would directly be used to update the weights. But since we're computing the weighted average of the past to compute the momentum idea for the momentum, to get the momentum. And so in the earlier training, such as when t is equal to 1, V0 would be 0. So this term would be basically 0. And the true gradient at t equals 1 is 0.1. But because of the beta, 1 will lead to 0.1. So in the earlier training, this term will become 0.01. So even though the true gradient was 0.1, in the very first iteration, we are going to update only using 0.01, which is 1/10. So it's basically there's an under bias problem, which we try to fix with the bias correction. And one concrete example here is just following this example, the under biased V momentum would be 0.01. But if we and we know that the beta is 0.9, and to the power of t, since t is 1, because t is equal to 1, the denominator will become 0.1. So for this specific example, after correcting the under bias, we're getting the we're lifting the bias to its original degree, which was not the bias. We're lifting the gradient to the original degree, which was 0.1. Is this part clear? Yes. So, and this idea applies also to the accumulation of the accumulation term, and all the other formulas are basically the same. We are applying momentum RMS prop with this bias correction to take care of the early training under bias problem of the updates, which those three constitute the ADAM. Okay. Yes. So we went over the we finished the deep learning so far. So we will next go over the support the vector machine. We could take a 10-minute break. We can resume at 4:05. Yeah. The support vector machine. Okay. I hope everyone came back. Okay. Yes. Before diving into the support vector machine, we want to first get familiar with the concept of the linear classifier, and one way to understand it is revisiting the logistic regression, so which you guys may have learned by Jacqueline. So the logistic regression itself is not linear, because go through a S curve between 1 and 0, but it's in fact a linear classifier, because it's basically squashing. We first get the logit, the linear combination between the weight, the input. So we are basically squishing the logit, which is unbounded, into the bound of 1 and 0. And for the logistic regression, the threshold is 0.5. So this indicates that when we could forget about the bias term here, indicates that when Wx is equal to 0, which is basically z, this term will be 1, which is 1/2, which when z is logit is 0 is 0.5, meaning all the logits that are above 0 will translate into above 0.5, and all the logits that are lower than 0 will translate into less than 0.5. So basically, what determines the classification when with threshold 0.5 is this linear function. Despite, even though the classifier itself in its when it comes to the logistic sigmoid function is nonlinear. So this is basically the linear classifier, which we will also use for the when we go over the support vector machine, and we call it as a g of x. So we will call this as a linear classifier or discriminant function, or even a score function interchangeably. So for the linear discriminant function, we saw the formula. We are basically having a d-dimensional feature vector with a weight vector, which is also d-dimensional. And the learning task here is, because this feature vector comes from the data, the weight vector is what we want to the parameter we want to estimate using the training sample. So the learning task is to optimize this weight vector. Which the linear discriminant function is basically brings the idea of the linear decision boundary, which if we set this as a constant, this will correspond to, in the feature space, a level set. So basically, when we set this linear discriminant function to some constant that translate into some plane in the 2D space, a line, and in higher dimensional space, a hyperplane. So if this linear discriminant function corresponds to a line or a plane or a hyperplane in the feature space, that indicates that we are dividing the space using that hyperplane, which naturally aligns with serves as a discriminant function, because there could be data points here and there beneath the decision boundary, so we're dividing them. And the discriminant function also comes with this bias term. So we will go over in the next slides, but basically in the 2D feature space, the weight vector will dictate the orientation, the angle or tilt of this line, whereas the bias term will corresponds to a shift with respect to that orientation of the plane. Right. So just to give a quick idea, is it's not a good thing. If the weight vector, if the linear decision boundary that corresponds to this function becomes this line in the 2D space, then its orientation will be perpendicular, normal. This is dictated by the weight vector, and whether it passes the origin or not will be dictated by the bias term. So here there will be a small amount correspond to the bias term, which is W0. Yeah. Yes, so yes, this slide is basically saying the same thing what I said, that we'll have a input vector, weight vector, which is both in the same dimension of D, And this will correspond to a linear decision boundary. In this case, the D is equal to 2, which is 2D feature space. Serves as this boundary for different classes. So our task, assuming for a two-class case, is that we simply want to find a line, a decision boundary that can divide between different class samples, such as we want here, it did a successful job of dividing the data points of the dot or the circle versus the class X. So we want to find such a decision boundary. And since we set the discriminant function as 0, we want so one thing to look at it is that if we have a data point and we have a decision boundary, let's say this data point is x10. So we're basically plugging in this data point into this function, which will determine the distance, the scale distance from this decision boundary. But for x20, another data point, the output of this function when plugged in x20 could be negative. So in this case, the g of x output is negative. And in this case, the g of x output when plugged in x of 10 is positive. So this is basically how we discriminate samples with respect to their position with respect to the decision boundary by computing their relative distance to the line. Yes. If there's any questions or doubts, please let me know, or you could leave it as chat. So there are some data that are inherently linearly separable, whereas some data are not linearly separable. Where, for example, for this data set, there is no way to divide the circle class against X class using a line. They are not linearly separable. So this data that are linearly separable are, as in the previous slide, look like this. So this is the concept of the linear separability. And today, the support vector machine that are included in the slide are applicable to this type of data that is linearly separable. Before diving in, I would want to first mention that there are different types of support vector machine, which the one that we will go over today is a hard margin support vector machine, which assume that the input data is linearly separable. And so soft margin SVM is another type, which actually the other type is an extension of the hard margin SVM, allowing for some slack, meaning, in other words, the soft margin can handle data that is not linearly separable. But to demonstrate the concept from the beginning, we will cover the hard margin SVM because the soft margin is an extension of it. But in practice, the soft margin one is more used, and all the hyperparameters you see in a machine learning libraries such as scikit-learn are implemented with this soft margin SVM because the real world data is rarely linearly separable. Yeah. Right. So when we are given a linearly separable data, then we already went over the fact that from the discriminant function, the weight vector is what determines the angle of the decision boundary, the line in the 2D space. So, and also the bias is what determines the shift from the origin with respect to the direction of the weight. So in other words, the weight is the normal vector of this hyperplane, which is the perpendicular direction. Hyperplane. And the bias shifts by this degree from the origin. So we want to find the optimal weight and bias. And in this case, for linearly separable data, finding such a case, such optimal solution is not trivial because, which is demonstrated in this plot, is that in this region, there will be many different types of combinations of weight and bias, which is line, but we want to know the best one. And this is important because we are determining this line based on the training data. The learning task is to find the optimum line like this based on the training data. But so our machine learning model is going to be used in a test data setting, an unseen data setting. So, and there will be some variation in the between from the test data and the training data, meaning that let's assume that we somehow determine the best solution vector is this line, this blue line. But in the test data set, because the training data set and test data set can be different, one data point comes to here, this part. This is test, training. In this case, the decision boundary obtained by training failed to correctly classify the test data point. But we could have done better if we determined the linear decision boundary somewhere here instead of a line that's closer to the green part. Then there's some slack here, which even though the test data point is closer to the decision boundary, it would still be classified. So this is an example why coming up with arriving to this good best decision boundary is practically important when dealing with the test data set. Okay. So since now we have the task of finding the best uh, decision boundary or the weight bias combination. This is an optimization problem, and also a constrained optimization problem, which we will go over the constraints as well. And the optimization problem, when it's constrained, we could apply the Lagrange multiplier, which converts the constraint optimization problem, which is maximize some function subject to some constraint. This form is a constrained version, but by applying the Lagrange, we could make this into this unconstrained version, where we are incorporating the constraint into this objective function so that we can optimize this directly. But for SVM, the Lagrange multiplier is designed for equality constraint, such as one example is equal to 0. But in the SVM, the constraint that we will go over is an inequality constraint, which is g of x is greater than equal to 0. And for that reason, the KKT condition is an extension of the Lagrange multiplier framework that is designed to handle also the inequality constraints. So in practice, this, when we converge to some weight vector, optimal weight or bias, unlike linear regression, because the optimization problem is more complex, we don't directly derived, meaning we don't get an analytical solution directly, but we approach it to it iteratively, such as we do with the gradient descent-based search. Yes, so that's the key takeaways from this slide. So for the decision boundary, linear boundary, yes, this is what I mentioned earlier, which is that the decision boundary, this line is basically corresponds to the linear discriminant function being equal to 0, and all this above region is where g of x is greater than 0, and the below region are where g of x is less than 0, and this vector, the normal vector, is basically the weight vector, which we have discussed also in the earlier slides, which is perpendicular to the plane. And this is the perpendicular is important as a prelude, is because we want to calculate the distance from the plane to each data point. So the correct distance, which is also the shortest distance from a line here, would be the perpendicular one. So that's why we care about this normal vector, the normality. Okay, so this slide is Yes. So as I've just mentioned earlier, we care about the distance from the line to each data point, and we compute that distance using the g of x. Okay. Any questions so far? Okay. Yes. So as I've mentioned earlier, we are yes. So this is one example that we'll go over of how exactly we compute the distance from the decision plane, this line, to this off-plane data point x, which is here. So the distance will be basically, we're trying to get the, I think one student came in. Okay, so the distance would be basically the shorted distance, the perpendicular distance, and the direction that determines that perpendicular distance would be the normal vector, which is the weight vector here, which is shown as here. So in other words, to compute the exact distance, we would want to care about both the scale, the units, how many units is away from this hyperplane, this decision boundary, and also its direction, which the direction is dictated by the weight vector. Yeah. Right. So this is exactly uh the the displacement from this big X to the XP when we project the X onto this decision boundary, it will be XP. So we're trying to get the displacement vector from X to XP. That's will be the goal to in determining the distance of this data point of X from the linear decision boundary. And this slide is just to the formal way to do the just indicating that we are getting the position vector for X and XP and performing the standard vector subtraction. Yes, so this slide could seem very convoluted, but if we go to go over this step by step, is that the R here indicates the true distance, true geometric distance. So for now, we can just think this as the actual true distance. So basically, the displacement vector from xp to x would be, we not only need this r term, but also we need the direction, which the direction, as we discussed earlier, is dictated by the normal vector, which is w. So in order to get this displacement vector, we are multiplying r to w, but we are also dividing it by this term, which this term is not an absolute term, but this is the norm of w, the L2 norm of w, which basically this is the length. So we're dividing, what we're doing here is we're basically normalizing this vector into a unit vector. so that we can get the displacement vector that represents the true distance for r. So now, since we have the displacement, x dot is the basically xp up to x. We can represent the data dot x as the vector addition of xp plus this displacement, which is equivalent to xp equals to x minus displacement. And yes, if anything is unclear, please stop me. Yes, so now we have the representation of xp, which is on the decision boundary, in terms of x, which we want to compute the distance for. And we know that all points on the decision boundary, the level set equal to 0, which we can plug in xp, this term, into the discriminant function, which is this term. Is everybody following me? Right. So if we replace this x is the generic x, xp, which is basically plugging this in. And this this is basically the square of the L2 norm because the numerator is just the square of each weight, whereas the denominator is the square root of it. So this term just becomes this term, which is equal to 0. So if we pass this to the other side, it arrives to this the next this formula. So what we can it is what this to interpret this is saying that when we plug, so in the earlier I mentioned that when we want to get the distance from the linear decision boundary to a particular data point, we are basically plugging in that data point into x. So this function, this represents when we are plugging this data point x, the big X, into the discriminant function, which is, in other words, a score function, meaning it's computing the distance from the linear decision boundary to the x. which is now we got this expression, which is saying that the distance from the linear decision boundary to this dot corresponds to the r, the true geometric distance, multiplied by this the length of the weight vector, the L2 norm, which the length of the weight vector L2 norm is basically scaling the true the distance. So g of x does output the distance, but it is unnormalized. It is a scaled distance, not the true distance, where the true distance is based on the unit vector. So that is the reason why in the next slide here, I think maybe, yes, so up until the previous slide, I think we're clear that g of x when it's the right-hand side term is the scale distance, and to get the true distance, we want to normalize it by dividing it by the L2 norm. So R is now the true distance from xp to x, which we care about and will be used important case in the for SVM. Okay, so that would be the main takeaway. Right. So yes, and also the distance is basically when we talk in terms of an individual sample, we call use the term margin as just the distance from that data point to the decision boundary. And we're talking in terms of a set of samples, then the margin of that set of samples, we're referring to the smallest margin. So basically the closest, the distance to the closest data point within that set of samples from the decision plane. So, and that is in fact called the support vector. Which this I we will go over it again in the next slide. Right. So now we understand what a margin is. So when we are talking about a set of samples, margin is the distance from the closest data point, which here it's a little ambiguous which one is closer, but let's just assume the red, this one is closer. So for class of green circles, the margin is this distance. And for the class of X, blue X's, yeah, let's assume that this is closer. The margin is the distance from the decision boundary to this data point. And SVM is trying to find basically the max margin for each class. And one caveat here is that, so SVM, we're really not caring about other data points for each class. We only care about the closest, the data point that relates to, corresponds to the closest distance, which is the margin for that set of samples. And this data points are basically called support vectors. That's why it's called the support vector machine. Yes, so now we know have a visual understanding of SVM. Right. So yes, so as we have discussed in the earlier slide, we're trying to find that decision plane that leads to the maximum margin, unlike the other dashed lines, which have very small margin. And this is to we're trying to get some buffer zone so that even when there's some variation in the test data set, we trying to safeguard our linear decision boundary in from misclassification. Yep. Yep. So the training when we the problem itself is that we are given many labeled data points, and this is we are doing a binary basically doing a binary classification where each data point is labeled, and numerically we're expressing it as 1 and -1 instead of 0 or 1, which could be the case, but we are setting it as -1 and 1 because that will lead to a more advantage when we try to set the constraint later on. And we're trying to find a hyperplane that best separate that. Yes, so we have we understand that the distance, the shorted distance from the separating hyperplane to the closest positive or negative example, this part, the closest positive or negative example, is the support vectors. And the shortest distance are the margins. So this is the margin to the positive side, and this is a margin to the negative side. And one caveat here is that the support vectors will determine, you think of it as an upper band for the buffer zone. This is the buffer zone, which is hyperplane of H1. And another support vector for the opposite class determines the counterpart, which is H2. So we have three hyperplanes. One is the central hyperplane, H, which is where the discriminant function yields a score of 0, and H1 will yield a score greater than 0, and H2 will yield a score less than 0. And we want, so the distance between here, and you want to set the D plus and D minus the same distance. We want them to be equidistant because we're not favoring either one of the class. We want the hyperplane to be at the exact middle between H1 and H2. So basically, we are maximizing the 2D. And when we're trying to maximize this 2D, yes, so the takeaway from this slide is that we would first want to define, because we already know that, what's going on? Yes, I will a little bit speed up. So we know that this g of x is equal to 0 at here. And at H2, we discussed that it's the score, the distance is greater than 0, but we know that we call this as D and also D here. And since this distance is produced by this influenced by the weight vector, it's going to produce a scaled distance. a distance that is not the true distance, but a scaled by the weight vector. So it would be a scale distance of d to the positive side for this case. And for h1, which is the negative side of the central hyperplane, would be the opposite of a negative scaled distance. So yes, so this is basically the idea, which, yes, this is what I've just wrote, that the h1, the positive side hyperplane, is defined as this. Negative side is defined by this equation, scale distances. But now we can make these terms more easier to work with by leveraging the scale invariance property, which means that when the weight vector, let's assume that was 1, 0, and bias, let's assume that it's a 0, 1. And this is one set of the weight bias combination. And we could scale this by the factor of 2, each of them. And these two sets of weight bias combination in the feature space will correspond to the exact same decision boundary. The distances produced by this weight bias combination will be different, meaning it will be scaled by the norm of the weight vector as we see here. But they are basically, we will still get the exact same decision boundary, even the weight bias are scaled. So the decision boundary is invariant to the scale of the weight and biases, and this indicates that if we can have control over the weight and the bias terms, if we scale the weight and bias by some scale factor of 1 over this term and apply it here, then the right-hand side, this we can express it as 1. We'll still get the same exact decision boundary, but the right-hand side, it will be 1. Same, the -1 for the other h2, which now these numbers are easier to play with. Yes, which is basically what this slide is saying. We use the scale invariance property to scale down to the 1 and -1. So now we know that this formally corresponds to, before scaling down. So this 1 and -1 in terms of the feature space is central is g of x equal to 0. h1 is g of x equal to 1 now. h2 here is g of x equal to -1. So now the distance between here is 2, because 1 plus 1, the distances are 1 each. But since these values are actually computed, are outputted, scaled by the weight, right? So these are not the true geometric distance, but still scaled by the weight vector. So that's the reason, as we have done before in the previous slide, we try to normalize this distance of now value 2 by the length of the weight vector. So we get the, yes. So now basically what we're trying to maximize the distance here, which corresponds to this expression. So it's the problem of max weight vector, and which we will see in the next slide, but we know that if we try to minimize this norm, it's equivalent to maximize this entire term. Yes, so we're trying to get the argument of minimizing, argument which are the weight and bias, minimizing the weight vector to maximize which, and we for convenience we set this as a quadratic problem here. So this is the reason for doing this is for gradients, for optimization, because an optimization algorithm will be applied in solving this. So which now the problem by doing this is a quadratic problem. So quadratic optimization algorithm will be applied to this, and if it's squared, then the gradient will just end up as, if we do get the partial with respect to some weight, then it would be, by the chain rule, we would get exactly Wi here if we transform it into this optimization problem. But if we directly apply it to here, there are some cases that are hard to solve, because when the weight vector is equal to origin, then we don't have a gradient there. So that would cause problem in optimization. So that's the reason why we make it into a quadratic problem. And also, we not only want to maximize the distance, but also we have a constraint that all of the data points should be correctly classified. Yes, which maybe I'm not sure I have enough time. So the idea is that the g of x, for a data point xi to be for its distance to be computed as the positive side, the discriminant function should output a positive value, and in order to be outputted above h1, above the safety zone, it should be greater or equal to 1. So if the constraint is active, meaning that the g of x outputs exactly 1, then that data point will be right on top of the h1, the non-central hyperplane. But if it's far apart from in a very safe area in terms of classification, it would be much greater than 1. It could be like 3 here, the distance from the central hyperplane. And we know that we set the true label in the binary class as 1 or -1, so that we could exploit the multiplication between these, because 1 times 1 is 1, -1 times 1 is -1. So if the product of these two terms are less than greater than 1, that means the data point, which regardless of whether it's in the negative side or positive class, is correctly classified. And that leads to this constraint. This constraint is saying that the data point is correctly classified in the right side, with not only correctly classified, but it's somewhere beyond the safety buffer, or right on top of H1 or H2. So this is, since our objective function is quadratic and the linear, this constraint is linear. So this inequality constraint, as we have discussed before, we can solve this in terms of optimization problem. This is a straightforward optimization problem, quadratic programming optimization problem, where there are many solvers for this. And the KKT condition, we're trying to solve it. The reason is because it's an inequality constraint, not an equality constraint. Yes, I know I'm a little rushing, but yes, I will just try to finish very soon. So when we try to formulate a problem, now we know that we can formulate the problem as a Lagrange, using the Lagrange multiplier. Now the objective function is quadratic, which we're trying to, Yes, sorry for the delay, but for the attendance, I will, actually, we are trying to do a different way of taking attendance. I will shortly finish this lecture and share the details. So yeah, I will, yes, get back to you soon. Yeah, sorry for the delay. Yeah. So when it comes to optimizing using the Lagrange multiplier, we have the objective function, and also we have the constraint, which we are trying to minimize this objective function with respect to the arguments of weight and bias, but also maximize the Lagrange multiplier, because the Lagrange multiplier is basically trying to penalize when the constraint is violated. So we want to penalize as much as possible when the constraint is violated, so the weights are pushed towards the feasible region when doing the minimization of itself. And the primal problem, which is the original problem, is a minimax problem. But the dual problem for convex functions, we can switch and lead to the same solution, which this has a nice property, which I will shortly go over. And the KKT condition, this detail, just to go over the very high level, is that solving the SVM problem is basically finding the KKT conditions, which we are trying to solve. So these are all the KKT conditions, and the first two are just saying with this Lagrangian, where we now have the constraint incorporated in it, we want to get the optimal W and optimal bias. These are the straightforward conditions. And also we want the Lagrange multiplier to be greater than equal to 0. And here the takeaway is that there could be two cases where the Lagrange multiplier is exactly 0 or greater than 0. So greater than 0 is basically activating the constraint, influences the constraint, which in terms of the hyperplane, we only care about the support vectors, right? We don't care about any data points that are above or beyond this support vector, because it's not helpful in determining the hyperplane, the central hyperplane. So the constraint, the Lagrange multiplier, will only be greater than 0 when the data point I is a support vector, and it will be equal to 0 when it's some irrelevant data point in determining the hyperplane. And this is also saying the same thing, something similar. And yes, almost done. So usually the SVM that we went over is a hard margin SVM where the data is assumed to be linearly separable, but in the real life, real world data, the data is usually not linearly separable. So in such cases, there are two options, which one option is to go with the soft margin SVM, which is more widely used, which allows for handle such cases, nonlinear separable cases. Or one other way is to project the data, transform the data into a higher level dimension so that it's linearly separable in the higher level dimension, which, as expressed in this example, we transform the data, which is not linearly separable, but in the 3D space, it's linearly separable. So this is another way. So, but the problem is that in the original data space, it can be very expensive to transform the data into a very high dimensional space. But the Lagrange dual problem gives a shortcut, meaning that we don't have to explicitly transform all of each of the data point to the higher level dimension and then apply SVM, but instead we could directly apply. We could implicitly transform to the higher level dimension and then perform the SVM, which is if we apply, make the primal problem into a dual problem by making the min-max problem to a max-min problem and go through the derivation, now we get the dot product of xi here. This is the objective function after the derivation. So we could directly apply the kernel, which kernel is applying it in the higher level dimension in this case. So by applying the kernel directly to this dot product, we don't have to explicitly transform each x into the higher level dimension, but do something get the same effect by using this trick of applying the kernel directly to part of the objective function, which the different kernel types, available kernels are here, which we could find in the machine learning library as like scikit-learn. Yeah. Okay. Yeah. Sorry for the delay. And yeah, now we're going to try. We're going to take the attendance. So for the attendance, the Blossom AI, you could send an email to this email address in Blossom AI in this format. You could just use the phrase as to this address. You could make the title as support vectors are closest data points to decision boundary between classes, and then they will take care of it. Yeah, and I suggest you to send this email now because we're trying to do this to set a time window in terms of accepting the attendance. Yeah. Yeah, once you send the email, please write on the chat. Okay, great. And while you guys are sending the email, sometime this week, I will make a Brightspace post about the timeline of the second half of this course. including when we will take the quiz 3, quiz 4, and the assignments, the timings when I will release them, and also the final project details with the grading rubric. Yes, I will make a post sometime this week regarding them. And tentatively, the next quiz will be done in next Monday for the first half. Based on the content that I've covered, the deep learning and SVM, and the subject that I will cover on this Wednesday.